Hey guys, welcome to the recitation. Like I said, today we're going to talk about some problems in number theory from the second worksheet in combinatorics and number theory. So let's get started. Did you try any of the problems?
I did the one where it was relatively coprime. It was
which one? What number was that?
To prove any 10 consecutive integers are that two are relatively coprime.
Okay. Ooh, recitation 5. I forgot even to. Oh my God. What the? Sorry about that. Come on. All right, so let me write here recitation. Number theory 1. All right, here we go. So let's start talking about the problems. And I would like to start with, let's say, what problem was the first one? Was okay. This is a nice problem. Problem 9. Problem 9 says the following. So let me look at the list. It says that prove that among 10 consecutive integers, right? At least one is relatively prime right? Relatively prime to each of the others. So this was problem number 9, right? Did you try this problem? Did you have time to? This was a very nice one. So let's see. And we will use here this kind of sieving process, and I'll explain what it means. It's quite classical in number theory. So let's see. How are we going to use the sieving process, whatever that means? So let's look. So we have 10 consecutive integers, and I have to show that at least one of them is relatively prime to each of the others, right? That's the statement. Okay, now we can say that any common factor of two such numbers, you can find it, let me see. Yeah, something like this. Yeah. The idea is correct. Yes, Nadia. So, so any common factor of two such numbers, right, have to be, keep in mind that 10 consecutive integers have to be divisible by what? Well, by 2, by 3, by 5, or by 7. Is that right? Keep in mind, this is the starting point of the problem. This is the main observation, I would say. So any common factor of two such numbers have to be divisible by 2, 3, 5, or 7. Okay, well, therefore, it will be sufficient, so it it suffices, let's say, to show that among any 10 consecutive integers, right? At least one is not divisible, by 2, 3, 5, or 7. Agree with me so far, right? So that's what we need to show. Well, like I said at the beginning, let's do the sieving process. So let's so we proceed by what we call by the following, let's say, sieving, whatever this means in process. But I'm sure you understand what it means. Okay, here we go. This let's start with 10 consecutive integers. So first, we start with 10 consecutive integers. Right? Okay. Now what we're going to do is the following. We will remove those divisible by 3. So remove those divisible by 3. Okay, that's great. So there are either 3, how many of them are there? Those who are divisible by 3 in 10 consecutive integers. Just think of 2/3, right? 2/3, 2 or 3, maybe not quite. There are 3 or 4 of them, right? 3 or 4 of them. Just think of the numbers 1, 2 through 10, right? Divisible by 3, how many of them are there? Like 3, 6, 9, right? So three of them. All right. Well, among these, let's say, right, at least one or two, or 2 of them, right, are also divisible by 2. Right? So thus, if we also remove those divisible by 2, right? We have eliminated at most 7 integers. We eliminate, or let's say we have eliminated, we have eliminated at most 7 integers. Right? So we have eliminated, at least one number divisible by 5, right? In this way, at least one number divisible by 5. Okay, well, what are we left with? Can you tell me? We're left with what? Do you understand the sieving process? What I just did? I'm keeping eliminating numbers. I want to see who is divisible by what, and I'm just taking them out. So those were left with how many integers? Somebody said something here. Well, we have eliminated 7, so we're left with what? With 3 integers, right? So we're left with 3 integers. Right? Well, and at most 2 of the, and at most 2 of them can be divisible by 5 or 7. And that's it. That's the problem. You see, that was the main idea, to start this sieving process, to start with 10 consecutive integers, then remove those divisible by 3, then you'll see that how many of them were there, like, okay. And then from those divisible by 3, you have to look how many of them were divisible, but also divisible by 2. And also you remove those as well. So in this way you eliminate 7 integers, right? And from those eliminated, from those which were eliminated and were divisible by 3 and by 2, at least one of them is divisible by 5. And then we are left with 3 integers. And at most 2 of them can be divisible by 5 or 7. That's it. That was the problem. Is it clear for everybody?
Yeah.
So basically, like, what you're left with is the remaining integers have to be, or are co-prime, right?
Yeah,
Because
exactly.
you write out all the divisors essentially, and so therefore, all of the possible divisors of sequential integers 1 through, or any 10 sequential integers, right?
Yeah. So this is, keep in mind this idea. It's very, very nice to use this kind of sieving process. Anyway, let's get to problem number 10, I think, from the list. This problem 10 is pretty straightforward. It says the following: prove that. And by the way, I forgot to mention this problem 9 was a Putnam, what was it? Putnam B2, 1966. Now, the problem number 10 says the following: prove that the expression and this is the expression is this JCD of m and n, everything over n times n choose m, is an integer. This guy is an integer for all pairs n greater or equal than m greater or equal than 1. This was a Putnam, what was it? Putnam B2 in 2000. Okay, so let's look at this problem. Like I said, it's pretty straightforward. Well, it's quite clear what to do. Well, when you see the JCD of 2 numbers, what is the thing that comes into your mind? Do you remember we did something in the lecture about the JCD of something? Do you remember this lemma that we did? What we call the Bezout's lemma, right? So by Bezout's lemma. What did it say? There exists these integers, let's say a and b in Z, such that what? The JCD, so I can express the JCD of m and n as this a times m plus b times n. Right? Exactly. Yes, just like Nadia says, yes. And now let's start computing this. Let's write it. Next we have the following. So what do we have? We have that the JCD of m and n, right, over n times n choose m. So this guy can be written as am plus bn, everything over n, okay, times n choose m. And now we're going to write this in the following way. So this is am over n times n choose m plus b times n choose m. Well, at this point, when you look at it, clearly b times n choose m, well, we would like to see how we can express that. But in any case, that would be, that's clearly an integer, right? B times n choose m. But what we need to prove now is to show that, so we need to show that this guy here, a times m over n times n choose m, is an integer, right? We need to show this. And let's see how are we going to do this. So what we're going to do is follow. I'm just going to leave a times m outside, out of this business, and then I'm going to take care of the 1 over n, or maybe I should say m over n times n choose m. So we have the following. So note that m over n times n choose m, this guy here is m over n times, and now let's write n choose m. So this will be nothing else by writing by the definition. This is n factorial over n factorial times n minus m factorial, right? And this will be, if we write this a bit further, this would be n minus 1 factorial, right? This n on the bottom there will vanish, over, and the same goes for m over m factorial times n minus m factorial, which is nothing else than n minus 1 choose m minus 1, right? That's it. So now this implies that that this guy, the JCD of m and n, everything over n times n choose m, is nothing else than just a times n, oh sorry, n minus 1 choose m minus 1, right? Plus b times m choose n. Wait, what am I doing here? N choose m. Sorry, m and choose m. So, right? This guy is an integer, and that's it. That's the problem, right? That was the only thing you need to use. Bezout's lemma. That was it. There's nothing else. It's just that. Is it clear for everybody what we just did? That was a Putnam B2 problem. Well, for me, it was pretty straightforward. I mean, there is nothing to see here. Now, any questions regarding this problem, or is it clear? I hope it's clear, right? Okay. Now, let me do problem 11. Which says the following: let n, again, this one we have to look closely at it. Let n be a positive integer such that n plus 1 is divisible by 24. By 24. Prove that the sum of all divisors of n, wow, the sum, we will see that we'll have some arithmetic functions will be involved here, that the sum of all divisors of n is divisible by 24. That was a Putnam B1 1969. Okay. All right. So did you try this problem? So remember that a sigma of n, this function was the sum of the sum divisor function, right? And by the way, I would like to advertise my talk. I'll give a talk next Wednesday at the Math Club, and I'll be talking about this sum divisor function. We'll see that this is, it goes all the way to Riemann hypothesis. There is an equivalent problem, an elementary problem equivalent to the Riemann hypothesis, which involves the sum divisor function. Anyway, for example, let me just tell you an example about this function. Let's take n equals 6, for example. What are the divisors of 6? Will be, well, if we want a sigma of 6, will be what? The divisors are 1, 2, 3, and 6, right? So it will be 1 plus 2 plus 3 plus 6, which will give us what? Will give us 12, right? So this is the sum of divisors function. And we have seen that we can express this in terms of it's an arithmetic, it's a multiplicative function and so on. So we can just express it in terms of powers of a prime. All right. And now let's look at it. So if I have a positive integer such that n plus 1 is divisible by 24, then the sum of sigma of n is divisible by 24. Wow. So let's explore this. And let's do it step by step, let's say, easily, like without, all right. Let's see. So I have an integer. Okay, now let me consider, what if we have, so consider D1 to be a divisor, D1 be a divisor of n, right? Then we can say that n is, let's say, is d1 times d2, right? And d2, this guys is also a divisor of n, and d2 is also a divisor of n, right? So we can write them in this way. Okay, and now let's look at this. So I write this n. So now, if we show that d1 plus d2, right, that's sigma of n, is a multiple of 24, right? And let's say n is not a square, right? So this means that D1 is different than D2. Well, then the sum, right? The sum of all divisors of n, of all divisors of n will be a multiple of 24. Do you agree with me on this one? So if the sum of two divisors is a multiple of the 24 and they're distinct, then the sum of all divisors of n will be a multiple of 24. And now let's look very, very carefully here. We know that, let's go back to, and let's explore this because we've done this trick. So n is a positive integer such that n plus 1 is divided is divisible by 24. So what do we know? So we know that as n is what? Is congruent with 23 mod 24, right? So we're given this. It follows that. It follows what? Let's see, what do we get from here? It follows that n will be congruent with 2 mod 3. Right? Let me explain this. Why is this? Keep in mind that let me see. So it follows, okay, such that n is not a square, right? Is not a square. Okay, because here, because the squares are 0 or 1 mod 3. Right, let's keep this in mind. So we have that n is 2 mod 3 and n is not a square. So in this case, keep in mind that n is d1 times d2. So in this case, we have either d1 is congruent with 1 mod 3, right? So that d2 will be congruent with 2 mod 3, right? Or what else? What else do we have? Or the d1 is 2 mod 3, right? So that d2 is 1 mod 3. So we either have these two cases. Okay. Well, in both cases, if we add these two divisors, in both cases, okay, we have that d1 plus d2 is what? Will be 0 mod 3. Right? Okay. All right. Now, let's see similarly when we have, let's say, so we have 23 mod 24. Now, similarly, what if we have for n 7 mod 8, right? So that d1 so that D1 will be, must be what? If n is 7 mod 8, D1 will be congruent with what? Will be 1, 3, 5, 7 mod, or even, right? 1, 3, 5, 7 mod 8. Okay? And wait, let me think a bit. So I have D1 congruent is 1, 3, 7 mod 8. So, and in order to have D1, D2, right, the product, to be, well, because I know that n is D1, D2, to be 7 mod 8, right? It follows that D2 must be what? Exactly, 7, 5, 3, 1 mod 8, right? Must be 7, 5, 3, 1 mod 8, correct? Yes, right? Okay. And what does this mean? And in each of these cases, it will mean what? It will mean that we have what? What do we have? That D1 plus D2 will be what? Will be 0 mod 8. Agree with me? In both cases. Okay. So we'll have that this is 0 mod 8. So this implies that then we have what? Implies that D1 plus D2 is a multiple of, so is a multiple of 3, right? And a multiple of 8. So therefore, so it is a multiple of 24. And that's pretty much it, right? Is this clear for everybody? So that's what you need to prove. You need to prove that it's a multiple of 3 and a multiple of 8, and therefore it's a multiple of 24. And that's the problem. Anyway, I will skip problem 12. I will leave it for next week. I would like to do another, oh my God, I have to do some other problems as well. These are very nice problems. And let me leave problem 13 to the very end because, and let me go to problem 14. In fact, problem 14 is an immediate application of the order of an element, but anyway, I'm not going to talk about this. I'm just going to mimic the order of an element without even mentioning it. Problem 14 says the following: show that if n is an integer, greater than 1, right? Then n does not divide 2 to the power n minus 1. This is a very classical problem at this point, but it was a Putnam A5 1972. Like I said, this will be an immediate application of the order of an element. Jack, I have a question. Since you took the number theory course, did you talk about the order of an element in that course?
Yeah.
You talked about it, right? Okay.
Yeah.
Anyway, So I'll just mimic it without saying what it is. But I'm sure once you look at the solution, you'll kind of figure it out. So now let's assume by contradiction. So assume that n divides 2 to the power n minus 1 for some n greater than 1. So let's assume this by contradiction, and then we'll get a contradiction. All right, now let's see something about this guy, 2 to the power n minus 1. Well, about this, its parity, what do you think? Do you think it's odd, is even? 2 to the power n minus 1 is always what?
Odd.
Odd. Since this is odd, right? It follows that what? That n is odd. So at this point, we know that both of them are odd numbers. Okay, great. Let's see, what can we, well, what can we explore more in this situation? Well, not too much. So maybe we should consider something. This is actually a very standard technique, but for those of you who see this for the first time, I agree it's tricky, but it's pretty standard. So now what I'm going to do is, let me look at the prime factorization of n. And not just that, what I'm going to do is I'm going to consider, so let us consider that, well, Nadia, n divides 2 to the n minus 1, and 2 to the n minus 1 is odd, right? So there, it's n is odd, it's obvious. Okay. You cannot have something like 4 dividing 2 to the 4 minus 1, right? If you look at it. So it has to be odd, not even. Okay, and now what I'm going to do is let us consider P. So I'm going to consider now the smallest prime, factor of n. And pay attention because this is very important. So we have a prime factorization, and I'm going to consider the smallest prime factor of n. And now remember Euler's theorem. So by Euler's theorem, what do we have? It follows that what? That 2 to the power what? Phi of p, right, of that prime factor is 1 mod p, right? Keep in mind here, because p is odd. This is important, right? So since p is odd, we have this. Now, if let's say if lambda is the smallest positive integer, such that 2 to the, well, this is what I'm defining the order of an element. Anyway, is 1 mod p, but I'm not saying what it is, but then it follows that lambda divides, well, it will divide phi of p, but phi of p can be computed, and in this case, I gave you a formula for how to compute phi of n, but if you replace n by a prime number, phi of p, so the Euler's torsion function, it follows that phi of p is p minus 1. So this means that it means what? This means that what? That lambda has a smaller prime divisor, let's say, than p, right? But on the other hand, 2 to the n is congruent with 1 mod p, so lambda also divides n. So this means what? That thus we say that n has a smaller prime divisor than p, which is a contradiction. Right? So it cannot happen. You see, basically I just mimic the order of an element. So this is a very classical problem at this point. It's pretty nice. All right. Now let me do problem. What problem was? Let me jump to problem 15. Which says the following: let f be a polynomial. In fact, this is a very nice problem. Easy but nice. With positive integer coefficients. Positive integer coefficients. Prove that if n is a positive integer, then f of n divides f of n plus 1. If and only if n equals 1. So this was a Putnam B1 2007. All right. This is easier than you think. Well, but keep in mind, I gave you some time ago when we talked about polynomials, I gave you this lemma, right? There was this lemma that if f is a polynomial with integer coefficients, then f of x minus f of y is divisible by x minus y, right? For all integers x and y. So we're going to use this lemma. And the key observation by using this lemma, so the key observation is that, well, you can say that, okay, let me write it here. f of n plus 1 is, well, minus f of 1 is divisible by f of n, right? So we can write this in the following way: is congruent with f of 1 mod f of n, right? You agree with me so far? Okay. All right, so now, well, for n equals 1, guess what? It's obvious, right? So for n equals 1, it is obvious. So it follows that, okay, I'm gonna leave it to you. It's, right? We do have that f of 1 divides f of 1 plus 1. Just look at the observation. Just take n equals 1 in the above equality. All right. Now, for the other implication, conversely, suppose that by contradiction that n is greater than 1. So remember, we have to show that if that if f of n divides f of n plus 1, then n equals 1. Well, suppose by contradiction that n is greater than 1, and now we're going to use the fact that f has positive integer coefficients. So since f has positive integer coefficients, f is an increasing function on positive numbers. On positive numbers, positive integers, right? So this means that f of n will be greater than f of 1, right? It's increasing, and greater than 1 by assumption. F of n is greater than f of 1. Whenever n is greater than 1. Okay, great. But now let's use the key fact again. Okay, we're gonna have this. But we have that f of n plus 1 is congruent with 1, f of 1, sorry, right? Which is not congruent with 0 mod f of n. So this implies that f of n does not divide f of n plus 1, which is a contradiction. And that's very nice, right? You see, we have used this, the fact that f of 1 is not 0 mod f of n. So it follows that which will contradict the fact that f of n does not divide f of n plus 1, right? But we know that this actually happens, so we get a contradiction, and that's it. Okay, I think there was two problems, but I think I'm gonna stop here. Maybe, yeah, next week we'll talk again about number theory. I will talk about, probably I'll do 2 lectures as well. 2 lectures in 1 recitation, probably, we'll see. I would also like to talk about some analytic methods in number theory without talking too much about analytic number theory, but I'm not sure how much I can avoid it. So thank you very much. I'm gonna stop here.